Okay, hello, teacher. Today we're going to be presenting about the Routh Hurwitz criterion. We are from group 5. Okay, introduction. The transfer function can identify the closed loop poles, which are represented as the function shown here. The characteristic equation is shown over here. The necessary condition for stability is first, or the coefficient of the polynomial must have the same sign, which is if the sign is positive, of the polynomial must be positive, and if the sign is negative, of the polynomial must be positive. The second one, none of the coefficient vanishes. For example, all the power of s must be present in the characteristic equation. If it occurs, some coefficient vanished, we can assume that the system is unstable. If any polynomial satisfy the above two conditions, it is called a Hurwitz polynomial. Routh Hurwitz criterion. Okay, let's get into it more. An independent researcher combination between Edward Routh and Adolf Hurwitz. In 1876, Edward Routh proposed to efficient recursive algorithm to determine whether all the roots of the characteristic polynomial of a linear system lie in the left half plane. In 1895, Adolf Hurwitz proposed a method to arrange the coefficient of characteristic polynomial into a square metric called the Hurwitz metric, and show that the polynomial is stable only if the sequence of determinants of its principal submetrics are all positive. RH criteria is a mathematical test that is necessary and sufficient condition for stability on the LTI system. All the roots of characteristic equation lie in the LHP. It and only a certain set of algebraic combination of its coefficient have the same sign. This method involves tabulating the coefficient of characteristic equation in a particular way. Tabulating of coefficient give an array called root array. Interpret the root table to determine the number of poles in the right half of the S-plane.
Next is root array. Forming the root array characteristic equation of a given control system Fs equal A1s power n plus A1s power n minus 1 plus A2s power n minus 2 plus blah 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 plus an equals 0, which following the both necessary conditions. Next. Create the table which group the coefficient of polynomial in front of the s power n in odd power n even power in directly from characteristic equation. Third row, calculate from the first and second row. B1 equal A1 times A2 minus A0 times A3. Divide by A1. B2 equal A1 times A9 minus A0 times S divided by A1. B3 equal A1 times A6 minus A0 times A8 divided by A1. Similar to calculate the determinant and subtract, take negative sign the first column multiplied by the next column of its own position, then divide by the first coefficient itself, A1. Fourth row method is the same as third row, but use the value from row 3 and 4 instead. Also change the denominator to be do this process until Sn row, which we will get the constant term A, the last coefficient. Definition or the terms in the first column of the root arrays must have same sign. There shouldn't be any sign change in the first column of root array. Example 1. S power 3 plus S 6s squared plus 11s plus 6 equal to 0. And the solution is like on the slide. From stability criteria definition, there no sign change in the first column, so this system is stable. And in example 2, from stability criteria definition, there are sign change in first column, so this system is unstable. Number of poles in RHP equals to 2. Note that the number of sign change are equal to number of poles.
So the special case one. The special case one is that first element of any row of Routh array is 0, and the remaining row contains at least one non-zero element, which will make the next row become infinite and the Routh test false. Like as you see in this example, is that the last line of x power of 2 is occur the value of infinity, which we cannot calculate the next value anymore. So let's see the solution method. Solution method 1 is that substitute the positive epsilon value in the place of 0 in the first row of element. Do the Routh array until get the final constant value term with number epsilon, then take limit close to 0 to get the constant value. Like this example, we're following the step by step, which is we substitute the epsilon value to get the equation of epsilon term, and then take the limit epsilon close to 0 to get the constant value. And then do the Routh array as normal. So we can get the result of this system is that this system is unstable due to the sign change check in the first column. The solution method 2 is that inverse polynomial method. We will substitute S in original characteristic equation with 1 over C, take the LCM and rearrange the equation, then complete the Routh array. So as you can see, f function of S is that characteristic equation, and then we substitute S to 1 over C, and then rearrange the equation again to get function of C. And then we use the function of C to do the Routh array and get the result of the system, which is unstable like the method.
For the special case 2, let's go. For the special case 2, all the elements of a row in Routh array are 0, which cannot determine in the next row, as you can see in the last row. For the solution method, forming an auxiliary polynomial AS by using the coefficients above the Routh row to the table above. After get the auxiliary polynomial, take the derivative of auxiliary polynomial with respect to S, then replace the Routh by the coefficients of current equation. The concept of Routh is only occur in odd power of S. Therefore, the auxiliary equation is always formed in even power of S. The root of an even auxiliary equation are always symmetric to origin, as you can see in the 5 graphs. From the example graph, you can conclude that when the Routh row occurs, the system will be only 2 possibles, which is marginally stable and unstable. Due to the graph 1, 4, and 5, so that the system are unstable, and graph 2 and 3
are marginally stable system. This is an example of the special case too. As you can see that in the last row, s to the power of 3 is the Roth row, which is we can form the auxiliary polynomial by looking at the row on the top, which is the row s to the power of 4. So we can form as equal to s to the power of 4 plus 12s to the power of 2 plus 16, and we find the derivative of it and get 8 to the power 8s to the power of 3 plus 24s. So we replace the value back into the table. When row of zeros occur, we need to determine the change in the criteria of the stability. First, determine the sign changes in the first column. Second, determine by the roots of auxiliary equation. The Roth array will split into two parts by using the Roth. First is the part above Roth's line, and the other is below the Roth, which is included in the Roth itself. The root of auxiliary equation, as you can see, the changes sign in the system is equal to 0, so there's no poles on this right-hand side pole. And from the graph, we can say that this system is marginally stable.
So for the applications of the RH criteria, we can use the RH criteria in order to determine the overall stability of a system. Apart from that, there are certain applications of RH criteria. The applications: first, determining the range of values of parameter k. Second, marginal value of k, frequency of sustained oscillations. And the third one is determining the relative stability. So for this one is the application of RH criteria in determining the range of values of parameter k, as you can see. The roots of above equation depend on the value of k, as you can see in the picture of the closed loop system. We can determine the range of values of k for which the system is absolutely stable. Such a system is called as conditionally stable system. And this is the example. Determine the range of k for the system shown in the figure so that the given system is stable. For the solution, so we take it into the equation and we will get the characteristic equation, as you can see, s to the power of 4 plus 3s to the power of 3 plus 3s to the power of 2 plus 2s plus k equal to 0. And we use this equation to make a Routh array. For the system to be stable, there should be no sign changes in the first column. So k must be more than 0. So we get like in the picture. So k must be more than 0 and k must be less than 1.55. And the range of k for the system to be stable gonna be 0. K must be between 0 and 1.55.
And next, we are going to talk about marginal value of k and frequency of sustained oscillations. First, marginal value of k is that value of k for which the system becomes marginally stable. Second, for a system to be marginally stable, there must be a Roth in Routh's array. And lastly, the value of parameter k that make any rows of Routh's array as Roth is called as marginal value of k. Let's see the example. Open loop transfer function of a unity feedback system is gs equal k over s multiplied by s power 2 plus s plus 1 and then multiplied by s plus 2. Find the range of k for stability for what value of k that system will oscillate and what is the frequency of oscillations. For the solution, we can use the formula as shown in the slide. And the characteristic equation will be 1 plus k over s multiplied by s power 2 plus s plus 1, then multiplied by s plus 2 equals 0. Then the result, we will get s power 4 plus 3 s power 3 plus 3 s power 2 plus 2s plus k equals 0. And this slide will show the root arrays. We will bring up the equation from the previous slide, that s power 4 plus 3 s power 3 plus 3 s power 2 plus 2s plus k equals 0. For the system to be stable, there should be no sign change in the first column. So k more than 0. Next, we will calculate that 14 over 3 minus 3k over 7 over 3 more than 0. Then we will get 14 over 3 more than 3k. So that means 14 over 9 more than k. So the result is k more than 1.55. So k more than 0 and k less than 1.55. The range of k for the system to be stable is 0 less than k less than 1.55. And for marginal value of k, it is the value of k which makes a complete row in the roots array, a row of zeros. As you can see the root array in the left hand side of the slide, the row s power 1 will become a row if 14 over 3 minus 3k over 7 over 3 equal 2. The k marginally equal 14 over 9 equal 1.55. The value of k for which the system will oscillate is 1.55. So that means a is equal 1.8. A is equal 7 over 3 s power 2 plus k equals 0. And last but not least, let's talk about frequency of oscillations. In order to calculate the frequency oscillations, we need to calculate the roots of oscillatory equation at k equal k marginally. So we'll use the formula as k is equals 7 over 3 s power 2 plus k equals 0. Then we will put in k equal to k marginally equal 14 power 9. Then we will get 7 over 3 s power 2 plus 14 over 9 equal 0. And if we calculate all through the formula, through the equation of the formula, we will get s equal plus minus J 0.816, and you can see the plot of the graph right hand side of the equation. The magnitude of imaginary roots of auxiliary equation gives the frequency of oscillations. The result is omega equal 0.816 radians per second. And here is all for today. Thank you for your attention.